All right, so welcome everyone and welcome YouTube. We will be talking about the bootloader today. Um, we won't go too low level into our bootloader project, but we will give an overview of the bootloader project and what you need to know about it. So the bootloader is, at time of recording, still under active development. So some of the things that I talk about aren't going to exist yet, or they don't exist yet, but they will exist in the future. And so this is about the design of the project, and all of you lovely people can help with implementing a lot of it, actually. So that's what makes the bootloader exciting. All right, so what actually is a bootloader? So on the highest level, a bootloader is a program that starts other programs. So usually when a computer starts up, it's going to be the first thing that runs. It's not just an embedded thing. The BIOS is a bootloader on your computer. When your phone starts up, it jumps into a bootloader, which does a bunch of setup and then starts whatever. And so that's what a bootloader is. It does some setup and then it starts other programs. Yeah. By the way, if anybody has questions, feel free to interrupt me at any time to ask questions, or actually maybe not interrupt, but like ask questions. It's good. All right. So before we talk about how our bootloader actually works on STM32, so on our microcontrollers, let's talk about what actually happens before main gets called. Okay, so you normally think of main as like the starting point of your program, but of course there is stuff that happens before main gets called. It doesn't jump directly to main. So what happens is pre-bootloader, so we power on, and then what we actually do is we don't go directly to main. Instead, we go to the startup script, startup underscore stm32f072.s. The .s means it's actually an assembly file. So this isn't C, this is ARM assembly. Yeah, don't worry if you can't read it fluently. You have to like take a course on it to understand it. But what this file does is it'll get the memory ready. It'll set up some printing. It'll print the Git version stuff that gets printed. If you've ever flashed to a microcontroller or started up a microcontroller, you'll see that on Minicom. It's what does that. And then it calls main. So I'll actually show you it. This is what it looks like. It's a bit intimidating if you haven't seen assembly before. But it's fairly simple. All it does is it clears some memory and then jumps to a few different places in C code, and then it calls main. Yeah. But what happens when, so all of this is packaged into a single executable, and it's all flashed together. So this is all of what's in the package that gets flashed whenever you type make program with a microcontroller attached. So with the bootloader, we add an extra layer in between. So instead of jumping directly to the startup script, what we do is we jump to the bootloader first. And the bootloader is a totally separate executable sort of from the application code, which is what we call the project that is run on top of the bootloader, that the bootloader calls. So the bootloader, when it gets jumped into at power on, it can, because it's a totally separate executable, it doesn't rely on any of the application code to be there for it to function. So it can do things like manipulating the application code. It can replace it entirely. And it can also, do anything that a normal program can do. It can receive commands over CAN. It can, it can do whatever you like. And then it jumps to the application code, and then a project will actually start up. So that's the sort of super duper quick overview of what happens before we get to main, both with and without the bootloader. And then I want to talk a little bit about the flash layout here. So flash memory on STM32 is the part of memory that it's the part of memory that is persistent. So it's like a hard drive on your computer. The microcontrollers have flash. and we have 128 kilobytes of it, and it's where all of our code, it's where the code on the microcontroller is stored, and it's also where any persistent data is stored. So what we do is we take this 128 kilobytes and we break it up into 3 sections. The bootloader will take up the bottom 16 kilobytes of that, and then we'll have 2 config pages totaling 4 kilobytes, which I'll talk about in a minute. And then the application code, which is the which is the actual program, we leave the rest of the flash 108 kilobytes for that. So this not to scale diagram shows that one design constraint for the bootloader is that it has to be very small, because it has to fit in this 16 kilobytes, or as small as possible, so that it's not taking up, so it's leaving as much space as possible for the application code. All right, so that's sort of some of the low-level details of how it works, but why would we actually want to do this? So there's a bunch of cool things that we can do once we have this extra layer in between powering on and getting to the application code. So the main application here is flashing over CAN. So what that means is that we can actually send, because machine code for a project, once you've compiled everything down, it's just a bunch of bytes, and we can send a bunch of bytes over CAN, and the bootloader can receive a bunch of bytes from CAN messages. If you haven't encountered CAN before, CAN is our inter-car communication network, and it lets us communicate between microcontrollers and also external devices in packets of 8 bytes, so called CAN messages. So we can actually send the machine code for a project over a bunch of CAN messages to the bootloader. And because the bootloader is totally independent of the application code that it starts, we can replace the application code with the machine code that we're getting over CAN from the bootloader. And now, after we've done that, we've reflashed a board without touching it, which is really cool. And we can also, so that's the main application, because that could enable, really cool stuff like, we could fully reflash the entire car, upgrade all the firmware on the entire car really quickly, when before it would take, if we're on site and we've got all of our boards in the car, it would require toting around a laptop to every board and opening up all the enclosures in order to actually change the firmware on the board. But with this, we could do it completely automatically. Yeah, it could even, we can even script interacting with the bootloader, you could think of, and we could put it on a Raspberry Pi and then enable like Tesla style firmware updates, where it just pops up with, there's a firmware update available, and then you select yes, and it goes and reflashes the whole car. So that's the kind of cool stuff that we want to do with the bootloader. Other operations that we could, other useful stuff that we can do with the bootloader includes, we can implement other stuff as CAN commands. So we could like figure out what projects are running on the controller boards, and figure out what controller boards they're running on, figuring out what versions of projects. So maybe we want to know, whether the steering board is running the latest version. And we can figure that out very easily with the bootloader, when previously it would require, physical access to the controller board. And we can also do things like, checking if certain boards are up, or pinging certain boards to figure out if they're still alive. All right, so we're now going to get into some of the design of our bootloader in order to enable all these cool applications. So we want to be able to flash code and direct our code that we're flashing to a particular STM32. So we'll need some way of addressing the microcontrollers, because there's many microcontrollers on the CAN network, and we don't want to, say, accidentally reflash the center console controller board at the time with, power distribution code. That would be bad because it's the wrong firmware. So we need some way of addressing the microcontrollers. But complicating this is that STM32s, they're not attached to a board itself. Instead, they live on these controller boards. So I have a controller board right here. So they live on these tiny boards. And those tiny boards can move around between hardware boards, like for particular applications like power distribution and MCI and solar. So we have a ton of these controller boards and they move around very frequently. The reason that we have this architecture is because the microcontrollers tend to die frequently and we need to replace them, and it's much easier to replace them when they're on their own board. So because they move around real frequently, we can't just say this is the power distribution STM32 and this is the center console STM32. Instead, we need to have a way of addressing these controller boards, which is independent of the board they're on. And we also want to store information about the projects that the boards are running. So, of course, we want to be able to, query and say, what board is running power distribution right now, what board is running MCI. So the solution is that every controller board stores this big struct in flash memory. So this is the config pages that I was talking about earlier. Yeah, this is what's stored in these config pages. So we've got this big struct, and so let's go through the fields of it. So we've got, don't worry about the CRC32 for now, it's just a hash to make sure that everything's all right. This controller board ID is a unique ID for each controller board, as you might have guessed. So we have, so even though it's a uint8 because of technical reasons, we can only have up to 64 controller board IDs, or actually 63. But that's a numeric ID of the controller board. So we can have up to 60 odd controller boards at a time, which is a lot, but that's more than we expect to need. But because it's not much fun to say like Solar is on controller board number 20, we also have a space for a name for a controller board so that we can give it a name and say like, okay, and instead we can say like MCI is on Romeo, and then Romeo is the controller board. So that's the reasoning behind that, because it's not as much fun to just refer them by numeric IDs. So we have names for controller boards. And then we have information about the project that's currently stored on the controller board and managed by the bootloader. So this is information about the application code. So is there application code present? And then if there is, what's the name of the project? So that's the project name, like MCI or power distribution, or even one of the smoke test projects. It's the name of the directory under the projects are stored under the projects folder. Then this project info is an extra string that eventually we'll be able to differentiate two boards running the same project with. It's not really used that much right now. And this git version is a string that's just stores the commit hash of the commit that we flashed from. If you're familiar with the git version that gets printed on Minicom when you plug in a controller board, then it's the same kind of thing. And the reason that we include this git version is because say we want to figure out what version we want to be able to figure out what version of a project is currently running on a board, so that say we can figure out whether we need to update it or not. Then we have information about the application code itself, so its size and in bytes, and then a hash of it. So CRC32 is a really quick hash and all it is it's used to make sure that the application code and the config itself and whatever that it's the hash of didn't get corrupted. So we compute the hash and then we compare it to the CRC32. And if they don't match, then we know something went wrong, because flash memory isn't perfect and sometimes a 1 flips to a 0. And all of this data, because we're being really, really safe, and this is at such a low level, and it would be really hard to debug any debug any failures in the bootloader. All of this data is stored redundantly on 2 different config pages, which are set aside for it. So there's a bunch of safety that goes on in reading and updating bootloader configs, so that if one of them gets corrupted, we can always recover from the other one. Is the reason that we have 2 separate config pages. Page refers to a flash page, so you can only Flash is partitioned into these pages, and you can read up on the details of how Flash works. All right. So we've talked a lot about how the bootloader works on a particular, just inside a controller board. But now let's talk about how we actually interact, we will be able to interact with the controller board. So because we're in order to actually interact with the bootloaders that are running on the various controller boards in our car connected over CAN, we're going to have a client script written in Python, which sends commands to these controller boards over CAN. So for an example, if we're flashing application code to a particular controller board, the client script will say, "Hey, controller board number 2, I'm going to send some application code to you," and the bootloader will respond. And we'll go into how this works in a bit. But this is the main architecture. The client script can send commands to any subset of the controller board. So what that means is that the client script can address any number of controller boards at once. So it can address, it could only address controller board number 1, or it could address all 3 of these controller boards here. And we'll see that in a second. And the controller boards respond back to the client script. From the bootloader's perspective, running on a controller board, it's like it has an exclusive relationship with the client script, because the bootloaders don't have to interact with each other. They only have to interact with the client script. And that's just to make it a lot simpler, because we only have limited memory on a controller board. We only have 16 kilobytes, I believe. All right, so the way that we actually interact with the way that this communication works is we've got this concept of a CAN datagram. And because we're sending an awful lot of data around over CAN, because remember, we could be sending up to like 100 kilobytes of data to flash the application code. It's a really big pain to try and deal with the packing and unpacking these individual CAN messages. Because if you'll recall, a CAN message can only store up to 8 bytes of data. So dealing with kilobytes and kilobytes, 8 bytes at a time, is really annoying. So instead, we've defined this higher level protocol called a CAN datagram. And a datagram can store up to 2 kilobytes of data, plus metadata like what controller board ID should receive. You should receive the datagram. So these datagrams are implemented as a series of CAN messages. So they're implemented as a series of CAN messages. So what that means, so this is all of the data that's stored in a CAN datagram. So what we'll do is we'll chop up all of this data into 8-byte chunks, and then we send those 8-byte chunks as separate CAN messages, one by one. And then we use some interesting stuff with the message ID of a CAN message in order to make sure that the controller boards that are meant to receive it and know what board it's from. So let's go through the fields of a datagram, just so that we understand how these work. So we've got the protocol version, which is just for backwards compatibility to make sure in case we ever upgrade it. Then we've got a hash of the datagram, a CRC32 hash again. So that's just to make sure that the entire datagram doesn't get corrupted in transport, because if a 1 flips to a 0 or a 0 flips to a 1, then the CRC32 hash will change. And then, then we'll know if something got corrupted. The important field to pay attention to is the datagram type, which is a uint8, which represents what kind of command or response does the datagram represent. So that could mean, that means, say if my datagram type is 2, it could mean that this datagram means I'm about to flash application code. Or if this datagram means 3, or if the datagram type is 3, that might mean, this is just an example. This could mean, my data consists of, a bunch of, my data consists of, the name of the project that's currently running on my controller board, or something like that. So this datagram type specifies what kind of data it is and what kind of command or response the datagram represents. So that'll be defined in an enum in C or Python. If you've worked on Baby Driver, which a tutorial session on Baby Driver will be upcoming in, I think, a month or so. If you've worked on Baby Driver, it's sort of like a Baby Driver ID. Then we have an array of node IDs. This num node IDs field is just the length of the node IDs field. So the node IDs are the list of controller board IDs that are addressed by the datagram. So if you'll recall, every controller board has a controller board ID. And so this is the list of controller board IDs that are addressed by the datagram. So that's the list of controller board IDs that should receive the datagram and act upon it. Or we can specify the special node ID 0 in order to have the client script receive the datagram. And then we actually have the datagram payload. And so this can be up to 2 kilobytes of data. And it's just an arbitrary bunch of uintates. And so I've been ignoring these things about protobufs written on the side. A protobuf is it's a thing out of Google. Mitchell talked about it at the MU onboarding session last week. So it's a protobuf is essentially it's a way of packing a bunch of data into binary, which is less annoying to deal with than just than defining something like this, where we have an exact width for every field and trying to unpack this and pack it ourselves. So these protobufs. So for example, this querying protobuf is a protobuf for one of the operations that I'll talk about later. But all of this data will provide it, say, some IDs, some names and such. Sorry about that. Then it'll get converted by protobufs, the protobuf library, protocol buffers is the proper name, into some binary, and we'll stick it in here. And this is just to make our lives easier so that we don't have to deal with specifying an exact binary format for all of this. Protobufs do that all for us. All right. So at this time, does anybody have any questions before I go through what all the operations with Bootloader are? All right. Okay. So I'm not going to talk about what the kind of stuff that we can do with the bootloader is. So we can either, so these are all the operations. So what an operation is usually the client script will send a command datagram to a bootloader or running on some set of controller board IDs. And then the bootloader will do something and then send a response datagram back. So that's usually how it works. So we've got ping, query, update ID name, jumped application, and flash application code. So ping is a simple life check. So all ping does is the client script will send a simple ping datagram. So I'll have a datagram type of, I don't know, maybe 1 or something like that. And it doesn't need any content. But then when a controller board receives that, it'll just send back a response saying, I'm alive. And all that means is, the utility of this is that we can just check whether something is alive and currently running the bootloader. So the next more interesting one is query. So a query operation, I showed you the protobuf for it over here. We're trying to see what controller boards actually exist on the CANT network and what projects they're running. So the idea with that is that maybe we want to see what projects are running, what are all the projects that are running power distribution, or what projects are running on controller board Delta or something, if Delta is a controller board name. So how this is implemented is, or how this will be implemented, is the client script will send out a datagram which contains a bunch of possible data that a board can match. So that could be like the board ID, the name, the current project, Git version info, all of those fields that you saw in the configuration from before. So the controller boards, then when they receive this datagram, they will check whether their board ID matches any of the board IDs in there, or whether their name matches any of the names that were specified. And then if they match any of that information, then they send back all of their config information over another datagram. So I'll actually show you the response protobuf. Yeah, so it's just consists of a single ID and name. Actually, can you guys see this? Probably. All right. Somebody tell me if you can't see this. It'll consist of an ID, a name. It'll send back all of its data. So, and then you can imagine that the client script can then use this data and print out like a readout of all of the controller boards that are on the network. So, this could be really useful for getting information about the state of all the controller boards from the command line. So you could just type like, I'll have an example of what the CLI command line interface could look like at the end. But you could just type, make query and then, or make boot query or whatever, and then get a readout of all of the controller boards on the network and what projects they're currently running and what versions it all is. So that's really interesting. The next one is sort of simpler, updating ID or name. We want to update the ID or the name of the controller board. So it's fairly self-explanatory. The client script just sends out a datagram that contains the new name or the new ID of the controller board that it's addressing. And the address controller board will update their config and respond back with an acknowledgement. So yeah, this one's not particularly interesting. The only complication is that, of course, we don't want multiple multiple controller boards with the same IDs on the network, because that would be bad for, because they both respond to the same datagrams, and that would be bad. So the client script has to ensure that that doesn't happen. Maybe by implementing this by doing a query beforehand and figuring out all of the board IDs on the network and making sure that that doesn't happen. So the really interesting one is, so this and the next one are the particularly interesting ones, jump to application. So when we're jumping to actually jump to the application, so the network part of it is the client script will send a command in the form of a datagram to tell controller boards to leave the bootloader and then jump to the application code. And the client script responds back with a command datagram, or the client script will send out a command datagram with a datagram type ID that says, jump to application. The controller boards will respond back with an acknowledgement and then jump straight to the application code. So there's an awful lot of low-level details in how this is implemented. So I won't, bore you with all of the details, but there's a bunch of assembly involved in how this is implemented. And it's really quite interesting in how we actually jump essentially to an entirely separate program. So there's a bunch of assembly involved. Anyways, and then finally, the really interesting part is how we actually flash the application code. So first, the client script will send out a datagram that contains a bunch of metadata, like the project name, the Git version info, and all of the things that it has, all of the, because the controller board, the bootloader has to update its config to say that, okay, my name is the project that I'm currently running is, maybe now it's power distribution or something. So after that, it sends the application machine code. So that's the compiled code for whatever project we're flashing in a series of datagrams chopped into 2 kilobyte chunks. So the reason that this was chosen is because 2 kilobytes, first of all, we can't send all of it at once in one datagram because we've only got 16 kilobytes of memory on the controller board. So we chopped the machine code into 2 kilobyte chunks. 2 kilobytes is the size of a Flash page. And you can read about how Flash works if you want to know the exact details. But it means that we can write it incrementally. So we can receive a 2 kilobyte chunk of application code and then write it all into Flash, and then clear the memory and then receive a new datagram and do the same thing. So yeah, so the controller board then will incrementally write the new application code into Flash when it's receiving these datagrams, and checking the CRC32s to make sure everything's okay. Meaning just, if anything's corrupted, we'll report it, and then we respond back with the status. And then we've actually flashed the application code over CAN, and that's the interesting bit. All right. So the last little slide I have here is an example of how the command line interface could look. Now, this isn't finalized yet. There's been very little work done on this high level of the Bootloader project, but these are sort of ideas of how it could look in the future, and you can help with implementing this. So we could ping boards with IDs, 5, 6, and 2. We could query for, say, we want to know if there is any board on the network with IDs 2, 3, or 4, or with names Alpha or Bravo, or running the Solar project or running the MCI project, and then we get a nice readout of what controller boards there are on the network and what their names are and what projects they're running and what version it is. We can update an ID. We can start meaning jump to the application on, say, all of our boards named after Pac-Man ghosts. So we can, say Inky is running power distribution, then it'll jump from the bootloader to power distribution and actually start the firmware project that we want to run. And then we can flash the board or boards with a single project over CAN. So we can flash, the board with the Alpha board with the BMS carrier project. So that's interesting. But the most interesting thing I think here is that we could implement we will implement a make boot update command. So what this would do is it would use a query operation to get all of the current projects and the IDs of all of the boards on the network, or all of the boards as specified, like boards with IDs 2, 8, and 12, get their current project, and then flash that board with the same project with whatever the current version is. So then we'd essentially be updating the entire controller board, or all of the controller boards in the entire car at once, and I think that's really cool. All right, so if you want to read a novel about the bootloader rather than watching me talk about it, then you can go into Confluence at this path and read the entire specification. But at this time, questions? Yeah, we do only have 4 minutes left, so if time runs out, then everybody just re-click the link and I'll stop the video. Right. So is it possible to get the STM32s to return to the bootloader through a CAN datagram, or does it no longer respond to the Python script while in application mode? That is a very good question. So that's something I didn't touch on, but yes, we are currently implementing that. So returning from the project to the bootloader so the current plan is that whenever the CAN library receives a bootloader datagram message, it'll jump back to the bootloader in order to process it. So in order to get it to then with that, it would effectively always respond to effectively if the Python script sent out a datagram, it would respond to it through the bootloader by jumping back from the application code to the bootloader. That also means that all the application code has to initialize and use the CAN library, but all of our projects do that anyways, except for trivial smoke tests. So it's not a big change. Are there any other questions? If you're comfortable, you can unmute and ask them or just put them in the chat. All right. All right. So I'm going to stop the video now, or stop the recording now. And yeah, goodbye, YouTube. So check out this Confluence page for more information.